Let's talk about Cartesian products in set theory. The Cartesian product of two sets, let's say set A and set B, is written as A cross B. It is defined as the set of all ordered pairs where the first element comes from A and the second comes from B. Formally, we have A cross B equals the set of the ordered pairs A, B, such that A belongs to the set A and B belongs to the set B. Notice that the order matters. The pair A, B is not the same as B, A unless A equals B. Let's see an example. Let's say A equals the set with elements 1 and 2, and B is the set X, Y. Then A cross B is the set of ordered pairs where the first element comes from A and the second comes from B. So we have an ordered pair 1x, then 1y, then 2x, and then 2y. So note that I'm getting first element of A, first element of B, then first element of A, second element of B, then second element of A, first element of B, and finally second element of A and second element of B. These are all the possible combinations of elements from sets A and B. In general, if A has m elements and B has n elements, then A cross B is going to have m times n elements. In our example, A had 2 elements, B had 2 elements, so A cross B had 4 elements. We can also extend this idea to more than 2 sets. For instance, A cross B cross C consists of ordered triples where the first element comes from A, the second from B, and the third from C. So if A is 1, 2, B is 3, 4, and C is 5, 6, A cross B cross C would be the set of ordered triples where the first element would be a triple with the first element from A, the first element from B, the first element from C. The second one would be a triple with the first element from A, the first element from B, and the second element from C, and so on. Okay, so we understood how to do Cartesian product, but let's take a step back and ask ourselves why we would do that. I recommend that you always make yourself this kind of question, otherwise you're just symbol pushing. So let's think of some applications for Cartesian product. First, the Cartesian plane itself is built from a Cartesian product. The set of all real pairs, which is R cross R, a Cartesian product, gives us the two-dimensional plane. Each ordered pair is a point on the plane. So without Cartesian products, we couldn't even define coordinate geometry. Remember, the Cartesian product is the mathematical way of saying, let's consider all possible combinations of elements from two sets. And this is essentially what we're doing here. We are considering all possible combinations of elements from R and R, which visually we can interpret as all points from R and R, which give us the ordered pairs that form the Cartesian plane. You can also think of relations between sets. So a relation from set A to set B is just a subset of A cross B. Why a subset? Because again, A cross B is the set of all possible combinations of elements from A and B, and a relation between these two sets is really a subset of this product. For example, let's say A is a set of people and B is a set of countries. And then we have Alice, who lives in Peru. The relation lives in is a subset of A cross B. So you could have L be the set which represents the relation lives in, of ordered pairs. Alice, Peru, and maybe John, India. Then we would have here also John, India. And this is actually a subset of the cross product. This, by the way, is the foundation of databases. A table of rows is really a subset of a Cartesian product of attribute sets. Think of a simple table of students. Mathematically, each column corresponds to a set of possible values. So you have the set of names, the set of ages, and the set of cities. The universe of all possible rows in the Cartesian product is names, cross ages, cross cities, which is potentially huge. Most of the combinations don't actually exist in the table. For example, the triple Bob 19 Paris is possible in the product, but is not in the table. The actual table data is then a subset of this Cartesian product. In this example, this is the table data, the subset of the Cartesian product, which has these three triples. This is why relational databases, we're talking about SQL, are based on relational algebra, which uses Cartesian products under the hood. When you run an SQL join, the database engine first forms the Cartesian product of the two tables, then filters rows according to your condition. So whenever you see a database table, think, all possible combinations come from a Cartesian product. My actual data is just a meaningful subset.